Optimization. Optimization are essentially absolute max and min word problems. I recommend that you go watch the video on how to find absolute max and min values if you haven't done so already. So in optimization with the word problems, I recommend the following procedure. That you first draw a picture and label completely, if possible. Sometimes there's not a picture to be drawn, but most times there are. Once you have your picture and your labels, use each piece of information that's given to help you come up with an equation of what you want maximized or minimized. For example, if I want to find the area, which we will do in the first example, I want to find an equation for area, because anytime I want to maximize or minimize something, I want to take the derivative of that something, set it equal to 0, or undefined, etc., etc., which is step 3. Take the derivative and find the critical points. And then, as we saw with absolute max and mins, use the critical points and endpoints to determine the max or min value. Now, sometimes I won't do this last step, and I'll talk about why when we get to the examples. So let's look at our first example. Suppose that a farmer has 300 feet of fence to make a rectangular enclosure which runs along a straight river. Let's get the picture started here. That'll be my river. And then I have a rectangular enclosure that I'm going to draw as well. Now we want to label this, so I will label that side X. I don't need to label the bottom side because the bottom side is river and no fence is needed. And then I'll label these sides Y. Now I'm going to use the information given, which says there is 300 feet of fence. So I know that X plus 2Y, using the labels or the variables that I chose, equals 300. There's no other information given, at least up here in the prompt, but I do know that I need to find the maximum area, which means I will want an area equation. So the area of any rectangle is length times width, in this case X times Y. So I want to take the derivative of this and set it equal to 0, undefined if necessary, and then do some more work. The issue right now is that my area is a function of two variables, both X and Y. But that's not a big deal, because I already came up with another piece of information here that has both X and Y in it. So I'm going to use this and substitute into my area equation. What you're going to see is so many problems have something like this, where you come up with the equation you need to maximize or minimize. It'll have two variables, so there'll be some other equation that helps you get what you want, that is this equation, down to one variable. So I know that area is X times Y, but if I look in my equation up here, I see that X is 300 minus 2Y. Make sure you see that as well. So area is X times Y, so I just need to multiply this now by Y. We want to take the derivative, but I'm going to multiply this out first to make my derivative a little bit easier to do. That is, I'd prefer not to do a product rule if I could. And we find that the area enclosed by this rectangular enclosure is given by 300y minus 2y squared. We want to maximize this. Okay, we know that maximum says take the derivative, giving us 300 minus 4y. I don't need to worry about undefined here, just 0. So we set the derivative equal to 0. And then just with a little bit of work, we see that y equals 75 feet. Did I answer the question? No, the question says, find the maximum area. Okay. Well, area is x times y. I'm missing the x, but I can find that by saying x equals 300 minus 2y. 300 minus 2 times 75, so x is 150 feet. I still haven't answered the question, which is, let's find the maximum area. X times y, which is 150 times 75 feet squared, which is 11,250 feet squared. Now, I came up with a critical point, and I assumed that was a maximum. I didn't do any work to try it out. Now, I could have done the following. I could have done a sign chart here, with 0 being the smallest y, and then really 150 would be the biggest y, because I have 2 y's and my total the fence I could have is 300. And then I could do some sign testing here, plus minus. So I know that this is a local max, but if I'm only increasing then only decreasing, it has to be the absolute max. Now, so just a couple notes on this. Generally speaking, if you're doing optimization problems and there's only one critical point, it's going to be what you want, the max or the min. If there's more than one critical point, I'd probably do a sign chart. But I knew I had one critical point, it's going to be my max. I knew this for another reason, is that the minimum area of a rectangle is 0. So if y was maximized, like I said, y, keep it the biggest it could possibly be, would be 150 feet. That would mean that x is 0, and that's going to give me a min. Regardless, whenever you're doing these problems, somehow convince yourself that what you found, in this case, my area, was actually a max when I asked for a max. Let's take a look at another problem, and what I want you to see in these problems is not differences, but similarities. Meaning, notice how I'm doing the same approach as best I can in all of these problems. Example number 2. Find the point on the graph y equals the square root of x that is closest to the point 4, 0. So I'm going to start by drawing a picture. And I'm going to draw the graph, or at least a decent graph, of y equals the square root of x. I'm going to plot the point 4, 0. And I want to find the point that is closest to this. Now, the key word here, of course, is closest, which we're going to translate into minimize the distance. That's what we really want to do in this problem. So when I know what I want to minimize, that tells me the equation I need to find. Now I'm going to keep drawing the picture. The minimum distance between two things is going to make a right angle with that. So the minimum distance is not going to be straight above the point 40. It'll be something along these lines, as drawn in the picture. And then I'm going to drop that down and form a right triangle with a base on the x-axis. And I'm going to start labeling this now. So I'm drawing a picture. I'm still in the labeling part. I want to minimize this length here. I'm going to call it R instead of D for distance. And then I want to find a label for this bottom part here, which I'm going to label as X, because a lot of people label that as X. But that is incorrect. When I'm labeling something and I have axes, x has to be the distance from the y-axis to wherever I'm trying to go. This case right there. Just like y has to be the distance from the x-axis to wherever I'm trying to go. So we shouldn't label this part x, but instead 4 minus x. Do you see why? Now we need an equation for the distance. Well, Pythagorean theorem says r is the square root of my base squared plus my height squared on my right triangle. Just like before, I want to find r prime, set it equal to 0, maybe undefined, but I have two variables. No worries. I already have one variable in terms of the other. So I can write this one as r equals the square root of 4 minus x squared plus y squared, which is simply x. And now we can take the derivative, because I have a derivative in one variable. So r prime, or dr dx in this case, which is, okay, we have the derivative of the square root of something is 1 over 2 root that something times the derivative of the inside part. That has the derivative of this piece. So I have 2 times 4 minus x times the chain out -1 plus 1. So where does this equal 0, or where is this undefined? Well, r prime is undefined when the denominator is 0. Convince yourself that's never going to be 0. Especially when x is a positive number up here. Which means I really only need to solve when the derivative is 0, which means where the top part is 0. So that's going to give me -2 times 4 minus x plus 1 equals 0. Or 2x minus 8 plus 1 equals 0. Or 2x minus 7 equals 0, so 2x equals 7. Or x equals 7 halves. Did I answer the question? It says find the point on the graph. Okay, all I found was the x part of it. Now I need the y part, but that's pretty easy because y is the square root of x. Let's take a look at one more. In this problem, we want to find the maximum area inscribed in one cosine curve and above the x-axis. How should we start? If you said draw a picture, I would totally agree with you. So I'm going to draw a picture of one cosine curve. You can choose any one. They're all symmetric. So I will choose the simplest one. That is the one that is centered near the origin. And then we're going to draw a rectangle. And I should have put rectangle here. Find the maximum area. And I'll add it right here, of a rectangle. That can be inscribed in one cosine curve and above the x-axis. So I have my picture. You know, I could have drawn it differently. I could have drawn it like this. That means there are many different rectangles that could fit. I just want to find the one that has the biggest area. So let's label. I'm going to label the non-dotted rectangle. The length from the y-axis to wherever I'm going, that's x. The cosine curve is symmetric, so that length would be -x. And of course the height is y, but the y is cosine x. So I'm taking all the information that I've been given. I haven't been given much, other than I have a cosine curve. But this is what I can do with my labeling. Now remember that we want to find an equation for the thing that we're maximizing. So I want to find an equation for the area of this rectangle, which is length times width, 2x times width cosine x, or base times height. Notice I went right to this. I could have started by doing 2xy like I did in the other problems. That's the area of this particular rectangle. But I'm getting used to it. I already know that I'm probably going to need to substitute in for one of the variables, so I just did that to start. Well, since I'm trying to maximize the area, we're going to take the derivative of area, which will be a product rule. So it gives us 2 cosine x, and then plus 2x times the derivative of cosine x. So I already know it's going to be negative sine x. Don't need to worry about where that is undefined, so we'll set it equal to 0. And then this is a calculator problem, so I'll go ahead and plug into a calculator, and I get that x equals 0.860. Again, like I did in the first example, I could check to see if this is really a max and not a min. But I already know, like if I had graphed it, this is probably not the real graph, but something along these lines. If this is A prime, and this is the 0.860, A prime changed from positive to negative, so I know it's a max. But usually when I get one critical point, it's going to be whatever I want it to be, in this case a max. I didn't answer the question, because the question says I want to find the actual maximum area. So I will go ahead and plug that x value back into my area equation right there. Still using a calculator. And I get that the maximum area is 1.122.